Right now, as you're listening to this, roughly 200 billion trillion stars are burning across the observable universe. That is a 2 followed by 23 zeros. And every single one of them is going to die. Not all at once, not in some dramatic cosmic explosion. The universe is far more patient than that. Current models suggest the last stars will burn out on timescales of around 100 trillion years, which sounds like forever. But here's what gets really wild. That moment when the final star flickers out is actually still pretty early in the full story of the universe. What comes after the last star is so much stranger, so much longer, and so much darker than anything that came before it. And tonight, we're going to walk through all of it. The universe is currently about 13.8 billion years old. In human terms, that sounds ancient. In cosmic terms, we are basically newborns. Astrophysicists Fred Adams and Greg Laughlin at the University of Michigan developed a framework for understanding this. They published it in 1997 in the journal Reviews of Modern Physics, and later expanded it into a book called The 5 Ages of the Universe. Their idea was elegant. Instead of measuring time in regular years, they used something called cosmological decades, where each decade is a power of 10. So cosmological decade 6 is 1,000,000 years. Decade 9 is 1,000,000,000 years. Decade 14 is 100 trillion years. Using this framework, they divided all of cosmic history, past and future, into 5 distinct eras. The primordial era covers the Big Bang and the formation of the first atoms. The Stelliferous era, which is where we are right now, is the age of starlight. It's when stars burn, galaxies spin, and planets orbit in the warm glow of nuclear fusion. We're living in cosmological decade 10, early Middle Age, and the Stelliferous era is beautiful, but it's also temporary. See, the stars we see in the night sky are not all created equal. Our sun is a middle-aged, medium-sized star. It'll burn for about 10 billion years total, and it's already halfway through its fuel. When it runs out, roughly 5 billion years from now, it'll swell into a red giant, engulf Mercury and Venus, and eventually shed its outer layers into a glowing planetary nebula before collapsing into a tiny, dense object called a white dwarf. That's a dramatic ending. But our sun is actually one of the flashy ones. It burns bright and dies relatively fast. The real survivors, the stars that will outlast everything else by trillions of years, are the smallest and dimmest stars in the galaxy. Red dwarfs. Red dwarf stars make up about 75% of all the stars in the Milky Way. 3 out of every 4 stars in our galaxy are red dwarfs, and you can't see a single one of them with your naked eye because they're so faint. They burn at a tiny fraction of the sun's luminosity, some of them producing less than 1/10,000th the light our sun does. If you replaced our sun with a typical red dwarf, the Earth would freeze solid. You'd barely be able to see the star from our planet's surface. But what they lack in brightness, they make up for in endurance. And it's not even close. A red dwarf with about 10% of the sun's mass can burn for 10 to 12 trillion years. That's not a typo. Trillion with a T. Proxima Centauri, the closest star to our solar system at just 4.24 light-years away, has about 12% of the sun's mass and will remain on the main sequence for roughly 4 trillion years. That's nearly 300 times the current age of the universe. TRAPPIST-1, that famous ultra-cool dwarf star with 7 rocky planets orbiting it, has just 9% of the sun's mass and could burn for anywhere from 4 to 12 trillion years. So what's their secret? Why do these tiny stars last so ridiculously long? It comes down to one word: convection. Red dwarfs below about 1/3 of the sun's mass are what astrophysicists call fully convective. Think of a pot of soup on the stove where the liquid circulates from bottom to top and back again. That's what's happening inside these stars. The entire star mixes itself, continuously cycling fresh hydrogen fuel from the outer layers down into the core and distributing waste helium throughout the whole body. They can use a far larger fraction of their hydrogen fuel than any other type of star. Our Sun, by contrast, can only fuse the roughly 10% of hydrogen sitting in its radiative core. It's like having a full gas tank, but only being able to use a cupful. Red dwarfs don't go out with a bang either. They never become red giants. Instead, over trillions of years, they gradually grow hotter and bluer as they consume their fuel, becoming theoretical objects astronomers call blue dwarfs. Eventually, they fade into helium-white dwarfs and go dark. Adams and Laughlin calculated that the very last red dwarf in the universe will exhaust its hydrogen fuel around cosmological decade 14. That's roughly 100 trillion years after the Big Bang. And when that final red dwarf flickers out, the Stelliferous Era is over. The age of starlight, which felt like it would last forever, turns out to be just one chapter. And here's where the story gets genuinely eerie. When the last star dies, the universe doesn't just go dark. It enters a new phase that Adams and Laughlin called the Degenerate Era. Not degenerate in the moral sense, degenerate in the physics sense, referring to degenerate matter, the exotic quantum states that hold up dead stars against the crush of gravity. This era stretches from cosmological decade 15 all the way to decade 39. For perspective, each of those cosmological decades represents 10 times more time than the one before it. The numbers stop meaning anything recognizable very quickly. Picture this. The sky, if you could even call it a sky anymore, is completely black. No stars, no glow on any horizon. Every star that ever burned, every star across every galaxy in the observable universe, is now a corpse. White dwarfs, the remains of stars like our Sun, are scattered across an impossibly vast cosmos. Each one is roughly the size of Earth but contains about half the mass of the Sun. Their density is staggering. According to NASA, a teaspoon of white dwarf material would weigh around 15 tons on Earth. These objects are made primarily of crystallized carbon and oxygen, held up against gravitational collapse by a quantum mechanical effect called electron degeneracy pressure. Neutron stars, the remnants of more massive stars that died in supernova explosions, are even denser. They're only about 10 to 14 kilometers across, roughly the size of a city, but they pack in more than the mass of our Sun. A teaspoon of neutron star material would weigh 4 to 6 billion tons. And then there are the black holes, the remains of the most massive stars, where gravity won completely. Alongside these stellar corpses are the never-wear stars. Brown dwarfs are objects with masses between about 13 and 80 times Jupiter's mass. They accumulated enough material to glow faintly, but never reached the critical mass needed to sustain stable hydrogen fusion in their cores. They're essentially failed stars, and an estimated 100 billion of them inhabit the Milky Way alone, slowly cooling toward the temperature of the void. And then there are the wanderers, rogue planets. Worlds that were either ejected from their solar systems by gravitational interactions or formed alone in the dark between stars. A 2023 survey led by Takahiro Sumi at Osaka University estimated that the Milky Way contains roughly 20 times more free-floating planets than stars. That's potentially trillions of cold, dark worlds drifting through intergalactic space with no sun to orbit. NASA's James Webb Space Telescope has identified intriguing candidates, including objects called Jupiter mass binary objects, or jumbos, drifting freely in the Orion Nebula, though their exact nature is still being debated. So the Degenerate Era is not empty. It's crowded with the dead and the lost, but it's dark, unimaginably, absolutely dark, and it's getting lonelier. Over timescales of 10 to the 19th to 10 to the 20th years, galaxies themselves dissolve. Through countless gravitational interactions between stellar remnants, about 90 to 99% of objects get flung out into intergalactic space, while the remainder spirals inward toward the central supermassive black hole. The Milky Way, the Andromeda Galaxy, the entire local group, all of it slowly comes apart. Meanwhile, dark energy drives the accelerating expansion of the universe, pushing everything that isn't gravitationally bound beyond each other's cosmological horizons. Structures that were once neighbors become permanently, irreversibly isolated. Every once in a rare while, something breaks the darkness. Two white dwarfs drifting through the void happen to collide. If their combined mass approaches or exceeds the Chandrasekhar limit, around 1.4 solar masses, the collision can trigger a Type Ia supernova under the right conditions. For a brief moment, there's light again, a flash in the endless dark. But these events grow very rare as the eons stretch on. Now, those white dwarfs themselves are not static, they're cooling, very, very slowly. When a white dwarf first forms after a star sheds its outer layers, it can have a surface temperature exceeding 100,000 Kelvin. That's almost 20 times hotter than the surface of the sun. But with no internal energy source, it just radiates heat into space and gets colder. The cooling happens in phases. First, there's a period of rapid neutrino emission, then a long, slow phase where photons gradually leak from the surface. Around 5 billion years in, something fascinating happens. The carbon and oxygen core actually crystallizes, forming a solid lattice structure, like a diamond the size of Earth. This crystallization releases latent heat, which temporarily slows the cooling, like how water releases heat when it freezes. Then finally, a last phase where heat capacity drops and the cooling accelerates. After roughly 15 billion years, the coolest observed white dwarfs have surface temperatures of just a few thousand Kelvin. The coldest one ever measured, an object cataloged as WD J2147-4035, sits at about 3050 Kelvin. But to cool all the way down to near absolute zero, producing a completely dark object called a black dwarf, takes at least 10 to the 15th years. That's a quadrillion years. A 1 followed by 15 zeros. And here's the kicker. The universe is currently only 13.8 billion years old. That means it's roughly 100,000 times too young for a single black dwarf to exist anywhere. Not one. They're purely theoretical at this point, objects that the math says must eventually exist, but that the universe hasn't had time to make yet. If you're still with me, and I hope you are because this is where it gets really wild, let me tell you about the last explosion the universe will ever see. In 2020, a physicist named Matt Caplan at Illinois State University published a paper in Monthly Notices of the Royal Astronomical Society that explored a surprising possibility that hadn't been widely considered. Even after white dwarfs cool to absolute zero and become black dwarfs, they're not quite done. Inside those crystallized carbon-oxygen lattices, quantum mechanics is still at work. Through a process called py-8no-nuclear fusion, nuclear reactions driven by quantum tunneling through the crystal lattice, the carbon and oxygen atoms are very slowly, over timescales that make a quadrillion years look like a coffee break, fusing into heavier and heavier elements. Eventually, they reach iron-56, the most stable atomic nucleus. As iron accumulates in a process called electron capture reduces the electron fraction holding the star up, the effective Chandrasekhar mass limit drops below the actual mass of the black dwarf. And when that happens, it collapses and explodes, a supernova, from a dead star in a dead universe. The timeline for this is almost beyond language. The first black dwarf supernovae, from the most massive candidates at around 1.35 to 1.41 solar masses, would occur at roughly 10 to the 1100th power years from now. Caplan himself described this by saying it's like saying the word trillion almost 100 times in a row. The last black dwarf supernovae, from the least massive candidates, wouldn't detonate until around 10 to the 32,000th power years. About 1% of all stars that have ever existed will end this way. That's roughly a billion trillion objects eventually going supernova in the dark. As Caplan put it, it's hard to imagine anything coming after that. Black dwarf supernovae might be the last interesting thing to happen in the universe. Nobody will be around to see them. Every black dwarf will be so isolated by the expansion of space that light from one explosion could never reach another. Each one detonates alone, in perfect silence, in perfect dark. But wait, there's a catch. That whole scenario only plays out if protons are stable. And here's where physics gets uncertain. The standard model of particle physics says protons should last forever. They're the lightest baryon, and baryon number is conserved. But a set of ideas called grand unified theories, or GUTS, predict that at incredibly high energies, the strong nuclear force, the weak nuclear force, and electromagnetism all merge into a single force. And in that unified framework, extremely heavy particles called X and Y bosons can mediate interactions that turn quarks into leptons, which means protons can decay. If protons decay, everything changes. Every atom in the universe, every stellar remnant, every rogue planet, every grain of cosmic dust, all of it eventually dissolves into positrons, neutrinos, and photons. The predicted half-life is somewhere around 10 to the 34th to 10 to the 41st years, depending on which model you use. After about 1,000 half-lives, roughly 10 to the 43rd years, essentially 0 baryons would remain from the estimated 10 to the 80th in the observable universe. Matter itself would simply cease to exist. Nobody has ever actually observed a proton decaying. The best experiment looking for it is the Super Kamiokande detector in Japan, a massive cylindrical tank buried 1,000 meters underground in the Mozumi mine, holding over 50,000 tons of ultra-pure water and lined with more than 11,000 photomultiplier tubes, all watching for the faintest flash of light that would signal a proton breaking apart. So far, nothing. For one of the most commonly predicted decay channels, experiments have placed a lower bound on the proton's lifetime at about 2.4 times 10 to the 34th years. But there's a next-generation experiment called Hyper Kamiokande with 8.4 times the detection volume of Super K expected to begin operations around 2028. Over years of observation, it will gradually push sensitivity to proton lifetimes of around 10 to the 35th years, deep into the range where several leading grand unified theories predict decay should happen. If you're watching this in 2026 or 2027, we might be just a couple of years away from one of the biggest discoveries in the history of physics, or from ruling out a whole class of theories. Either way, it matters for the death of the universe. If protons decay, matter vanishes long before those black dwarf supernovae can ever happen. The end game changes completely. Now here's a good place to pause for a second. If you're lying in bed listening to this and you're finding it weirdly peaceful thinking about the universe slowly winding down into nothing, you should hit subscribe. I make videos like this regularly, exploring the strangest and biggest ideas in science, and I promise we'll keep it exactly this chill. Alright, let's keep going. Because after proton decay, or after the black dwarf supernovae if protons are stable, we enter what Adams and Laughlin called the black hole era. By this point, in scenarios where ordinary matter has decayed, the only organized structures left in the entire cosmos are black holes, stellar mass black holes from collapsed massive stars, intermediate mass black holes from merged remnants, and the colossal supermassive black holes that once sat at the centers of galaxies, now drifting alone through an incomprehensibly vast and empty universe. And black holes might seem eternal, but Stephen Hawking showed in 1974 that they're not. In a landmark paper published in the journal Nature, Hawking demonstrated that quantum effects near the event horizon cause black holes to emit thermal radiation, now called Hawking radiation. A black hole is essentially leaking energy, particle by particle, into the void, and this means it's slowly losing mass, very slowly. The temperature of a black hole is inversely proportional to its mass. A stellar mass black hole radiates at roughly 60 nanokelvin, which is almost unimaginably cold, far colder than the current cosmic microwave background radiation at 2.725 Kelvin. This means that right now, all astrophysical black holes are actually gaining mass from absorbing background photons faster than they radiate, but the universe is expanding and cooling. Eventually, trillions upon trillions of years from now, the cosmic background temperature will drop below even the Hawking temperature of these black holes. And that's when net evaporation begins. The evaporation timescale depends on mass. A black hole with the mass of our Sun would take about 2 times 10 to the 67th years to evaporate completely. The supermassive black hole at the center of our Milky Way, Sagittarius A star, with about 4.3 million solar masses, would require roughly 10 to the 87th years. And the largest known black holes, like Phoenix A, at around 100 billion solar masses, with an event horizon spanning roughly 3,900 astronomical units, or ton 618 at 40 to 66 billion solar masses, would take on the order of 10 to the 100th years to evaporate. That number, 10 to the 100, is called a googol. It's where Google got its name from, actually. As a black hole shrinks, its temperature rises and the evaporation accelerates. The process runs away at the end. The final moments are expected to be a burst of high-energy radiation as the black hole shrinks toward the Planck scale. Although what happens at that exact point is still unknown, because it requires a theory of quantum gravity that we don't have yet. And then, one way or another, it's gone. The last organized structure in the universe, the last object you could point to and say, that's a thing, disappears in a flash of light that nobody will ever see. After the last supermassive black hole in the universe releases its final burst of Hawking radiation, Adams described what remains as a diffuse sea of electrons, positrons, neutrinos, and radiation. No galaxies, no stars, no planets, no atoms, just particles and energy drifting apart in an ever-expanding void. And that brings us to the end, the real end, the final era. Adams and Laughlin called it the Dark Era. The concept has a name that sounds paradoxically warm: heat death. It was first described by Lord Kelvin in 1852, formalized by Rudolf Clausius, who invented the concept of entropy in 1865, and dramatically named Warmatod, literally heat death, by Hermann von Helmholtz. But heat death doesn't mean the universe gets hot. It means the exact opposite. Heat death means that all energy in the universe becomes perfectly uniform distributed. Every temperature gradient vanishes. No region of space is warmer or cooler than any other. And because thermodynamic work requires a temperature difference, a flow of energy from hot to cold, no work of any kind can ever be performed again. No stars can form, no chemistry can happen, no computation can run, no life can exist. Not because the laws of physics forbid it in principle, but because there's no energy gradient left to power anything. It's like a perfectly still pond with no wind, no current, no ripples. Nothing moves because there's nothing to make it move. It's the ultimate consequence of the second law of thermodynamics, that entropy in an isolated system always increases, applied to the cosmos as a whole. The temperature of the universe approaches, but never quite reaches, absolute zero. The third law of thermodynamics forbids actually hitting zero, so the cosmos exists in a state of near zero temperature, near perfect uniformity for the rest of eternity. Physicist Brian Cox captured it when he wrote that nothing happens, and it keeps not happening, forever. There are a few last ghostly processes. Electrons and positrons drifting through this void may occasionally form bound pairs called positronium, exotic atoms where an electron and a positron orbit each other, held together by electromagnetism rather than gravity, at distances that could be larger than the current observable universe. These bizarre atoms survive for incredible lengths of time before the electron and positron finally spiral inward and annihilate each other, producing a pair of gamma-ray photons that redshift into oblivion. The timescale for the largest positronium atoms to decay is estimated at around 10 to the 176th years. After that, there really is nothing left to happen. The cosmic background radiation has been stretched to wavelengths longer than the observable universe. No structures exist. No meaningful flows of energy or information that could sustain any structure or process. Physicist Sean Carroll has described it by saying the arrow of time doesn't move forward forever. Eventually you reach maximum entropy and there's no more arrow of time. Now, before we wrap up, I want to mention something that could change this whole story. Because as settled as heat death might seem, recent observations are shaking the foundations. In March 2025, the Dark Energy Spectroscopic Instrument, known as DESI, released its latest results from Lawrence Berkeley National Laboratory. They've now mapped nearly 15 million galaxies and quasars, creating the largest three-dimensional map of the universe ever assembled, and the data is showing something unexpected. Dark energy, the mysterious force accelerating the expansion of the universe, may not be constant. It may be changing over time. This is a big deal. The standard model of cosmology, called lambda CDM, assumes dark energy is a cosmological constant, the same strength everywhere and everywhen. DC's year 1 results in 2024 hinted at something different. The year 3 results strengthened the signal, reaching statistical significance of 2.8 to 4.2 sigma, depending on which datasets are combined. That's not quite at the 5 sigma discovery threshold that physicists require, but it's enough to make a lot of cosmologists very nervous. If future observations confirm that dark energy changes over time, it could open the door to very different cosmic endings. Some models allow for a future collapse, sometimes called a big crunch. Others allow for runaway expansion that tears apart all structures, atoms and all, in a scenario called the Big Rip. But right now, these are still speculative possibilities, not established predictions. And there's another scenario that astrophysicist Katie Mack explores in her book, The End of Everything. If the Higgs field that gives particles their mass is sitting in a metastable false vacuum state, it could spontaneously decay, sending a bubble of destruction expanding at the speed of light that would rewrite the laws of physics as it goes. Researchers at the University of Trento in Italy actually observed an analog of false vacuum decay in laboratory systems for the first time in January 2024 using ultra-cold atomic gases. It's not evidence that our universe is about to undergo vacuum decay, but it shows that the underlying physics is real and testable. The European Space Agency's Euclid Space Telescope, launched in July 2023, delivered its first major data release of 26 million galaxies in March 2025, with full cosmological results expected in late 2026. Between DESI, Euclid, and the upcoming Proton decay searches at Hyperkamiokande, the next few years could fundamentally change our understanding of how the universe ends. The ending of the universe, it turns out, is still being written. And I think that's the most beautiful part of all of this. We happen to exist in the only window of cosmic history where the evidence for our own situation is even observable. Physicist Lawrence Krauss put it perfectly when he noted that we live in a special time, the only time, where we can observationally verify that we live in a special time. A few trillion years from now, the expansion of the universe will have pushed all other galaxies beyond the observable horizon. A civilization arising then would look out at the sky and see nothing but their own galaxy, alone in an infinite void. They would have no way to deduce the Big Bang, the cosmic microwave background, the existence of dark energy, or any of the cosmic history we take for granted. The evidence would literally be gone. We can see it. They won't be able to. That's a privilege worth sitting with. The universe gave us a front row seat to its own autobiography, and we showed up at exactly the right chapter to read the whole thing. A little earlier, and the cosmic microwave background would have been too hot to resolve. A little later, and the evidence would have redshifted beyond detection. We're here, right now, in the sweet spot. Carl Sagan once wrote that after the Earth dies, some 5 billion years from now, there will be other worlds and stars and galaxies coming into being, and they will know nothing of a place once called Earth, and that's true. But what's also true is that right now, tonight, in this brief flicker of the Stelliferous era, you are made of atoms forged in the cores of stars that died before our sun was born. You are the universe looking back at itself and asking what comes next. The stars will die, all of them. The white dwarfs will cool into black dwarfs. The black dwarfs might explode one last time in the dark. The black holes will evaporate, and then nothing will happen, forever. But right now, something is happening, and you're here for it. If this kept you up thinking or helped you drift off, either way, I'd love for you to check out the next video on screen. I think you're going to like it. Sweet dreams.